the angular acceleration in radians per second squared. Well, acceleration means change, the rate of change. What did it change? It changed from 1,000 to 3,000 to 1,000 revolutions per minute. That's a change of 2,000 revolutions per minute, but I wanted it in radians per second. Well, I know that for every revolution, every turn of a circle, there are 2 pi radians. If you don't understand that, you can come to me and talk to me about it, and I think I can prove it again. It's in the nature of a circle and the circumference formula for a circle. So 2 pi radians per revolution. This cancels out the revolutions. And I want it in per second. I want the seconds on the bottom because I want it per second. Plus, I know that I want to cancel out the minutes. So minutes must go on top to cancel out minutes on the bottom. Multiply by the top, divide by 60 on the bottom, should give you negative 209.3 radians per second. That's not the acceleration, that's the change in radians per second. It's not the rate of change. Did it do this in 1 second, 2 seconds, a whole day? How fast did it do it? It did it in 3 seconds. So we're going to take that number, divide by 3 seconds, and there is a slight error here, as the answer should be a negative to show that it was a deceleration, it was a slowing. And now I have it in radians, divided by 3 seconds, I have it in radians per second squared. Number 9, what's the centripetal acceleration in terms of g? Well, we need the acceleration centripetal toward the center formula, which is, of course, on the equations page. This is lowercase omega, and it is the angular speed, the angular velocity. Well, what was it? It's 420 revolutions per minute. That's how fast the speed that it's going around at an angle in a circle. Now, to get it in terms of g, I only really know g in terms of 9.8 meters per second squared. I'm going to have to get this in something that is more relatable. For one thing, I'm going to need it. And second, I'm going to need this revolutions things out of here. So I'm going to convert this. There are 2 pi radians per revolution. The revolutions cancel. And I want it in per second again. So the minutes cancel up and down. Multiply these two, divide by 60, gives me 43.96 radians per second. Now that's something I can use, and it will multiply correctly in here, because if I took revolutions times meters, it doesn't really work. I need radians times meters. Over here, the r is the radius, not the diameter. We have to take this in half, and we need it in meters. Half of this is 25 centimeters, but in meters, that's 0.25 meters, because the decimal moves 2 spots between centimeters and meters. Now, you may remember me saying that radians, to be picky, is not a true unit. It's merely a ratio of a distance on a circle's edge compared to its radius. It's not truly a unit, but if we don't write it, we can lose track of what we even have. So I'm going to take this value in radians per second, and remember it was squared. So this squared times 25 meters is why I get meters per second squared, because the radians do not square. They kind of disappear once I multiply by meters. They are just a placeholder so we can keep track mentally of what we have. They're not a true unit. The seconds do square, and the meters go on top. So this number squared times 0.25 meters should give me 483 meters per second squared. Now, that's pretty good, but the question asks for it in terms of g. How many meters per second squared is 1g trying to accelerate at? It's trying to accelerate at 9.8 meters per second squared, as we've said so many times. So in this case, if I multiply that, this is on the top now. All of this can be considered over 1, this whole thing over 1. Now, in that case, I have meters per second squared on the top, meters per second squared on the bottom. They all cancel out, leaving me a unit of only g. So this divided by 9.8, with all this canceling out, should give me 49.3 g. Now this washing machine can go 350 G. We're going to run this backward. And the washing machine drum is 55 centimeters in diameter. Of course, I can't use centimeters. I've got to use meters. And I can't use diameter either. I need radius. What's the angular velocity in revolutions per minute? This is all working backward. So 350 G, I can't use that. I got to get in something more usable. Remember the 9.8 meters per second squared? Per 1 G, the G's cancel out. This times that should give you this in terms of meters per second. Now, regarding this, what I'm really solving for, what is the angular velocity? I'm solving for the omega here. So what I've done here is I put the r under, and then I've taken the square root of everything. So W equals AC over R, but then all square rooted. This goes over here. What was the value for the angular acceleration? It's my answer from here. What is the diameter? It's half of this with the decimal moved 2 spots. Instead of 27.5 centimeters, it's 0.275 meters. This divided by this, all square rooted, should give me this. Now when I canceled the meters here, what I got was radians, because what I'm comparing is the distance traveled around the edge of the circle, and I'm dividing that, I'm comparing it by division to the distance of the radius. And what I do when I get that is radians. And we'll leave it there as a placeholder so we don't forget what we have. The second squared, square rooted, and the squared term came off. Now that I've got that here, I was asked for it in revolutions per minute. I don't really want radians, I want revolutions. So I'm going to flip this compared to the previous, and the 2 pi radians are at the bottom. The radians are going to cancel, so to speak, and leave me with revolutions. In this case, I don't want seconds anymore. I want the seconds on top to cancel this seconds on the bottom, and I wanted per minute, so I want minutes on the bottom. So this number divided by 2 pi times 60 should give me 1,067 revolutions per minute.